Hello again. Excuse me. Sorry. Okay. Now, I just wanted to begin this series with yet another uh, pleasant photograph to look at, and I want to mention one thing, I guess, about mathematics, that I guess most people know and understand, which is that mathematics generally deals with abstractions, idealized objects and whatnot. And some people may find that idea frightening, and think that it's too strange and they couldn't possibly understand all these weirdo concepts. But I'm just going to put it plainly that we do that all the time, human beings. There's nothing unusual about an idealized representation of something. Every idea that you have in your head is, in fact, and it's quite easy to prove to yourself that it's true, is some form of idealization of something that might or might not be real. Like an apple. If I tell you, I bought some apples yesterday. You don't, in your mind, think of a concrete, definite, specific apple with all of its features in detail, because your mind has abstracted the idea of an apple into an idealized thing, like a category, and you don't. It's not an unusual thing to do that. That's all I'm saying. We do it all the time, and it's perfectly normal. There's nothing to be afraid of in math. A line is an idealized concept that's similar to a piece of string. A surface is like a piece of paper. There's nothing especially in geometry that a person shouldn't be able to grasp fairly easily. The difficulty arises when the abstractions are things that are unfamiliar, not things that you have an everyday analogy for. But none of that exists in Euclidean geometry, so the geometry that you're about to see should all be in terms of ideas that you're already familiar with and have been for years and years. Now, first, here's this here. I've cleaned up my desktop. I have an ability to put programs in here. So there's only one thing available to click, and this here is my Magic program, which has many nice features. For one thing, I can make it big, like that. And that certainly helps in seeing things. It doesn't. I can draw lines and shapes and whatnot, and they're not perfect, but it's good enough. It's, like if I draw a thin line, choose a color white, say. It's not. It's going to be jagged, you know. You see, it's got this. It's not what they call anti-alias. And actually, it'll look better in this view. Not much better. And that's just a property of the functions that I use to draw these things, the Windows functions. That, as far as I know, don't support things like anti-aliasing. But it's okay. It doesn't need to be perfect. Delete that. Another thing I can do with this is change the background. I just made this one, and that helps. I think makes things look nicer. I can also get rid of the axes like that, which I want to for this first lesson. First, Euclid. This version of the first 6 books of Euclid, I downloaded off the internet. I'm not sure when this introduction was written, or even by whom. But actually, I think I do know. It says something here. Oliver Byrne. Okay. Etc. 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 Oh no. Yeah, that's who put this together. To the Right Honorable Earl Fitzwilliam. By Oliver Byrne, surveyor of Her Majesty's settlements in the Falkland Islands. So, and in 1847, this here, I think it must be London, Ontario, because it says University of Toronto. Okay, not important. Although the introduction is quite enlightening in some respects, the description of the point here I found quite enlightening and actually useful in understanding some of the notation that's used. The idea, I don't know if this, I doubt that Euclid did this, but the idea with this book is that they've chosen to use colors and shapes together with symbols, but more colors and shapes to represent the things being talked about, and with the idea that helps people to understand more clearly. Instead of having to keep referring back to the diagram for the letters, it's very, when you see this, that it's talking about that, right? But if you saw it, this equals this, then you have to, right, go through the diagram and try to draw it out. So actually, I think this method of communication is quite good. It might look childish, but I think it's actually a good and accurate system for communicating these ideas. And there's nothing wrong with being childlike. After all, knowledge and learning things should be fun. Okay. Now this really is the part where it's Euclid, and he begins with definitions. Some of the definitions are a little bit self-referential, I would have to say, but I think there's a point at which it's either you get it or you don't. We don't have more basic words to describe. It's like an apple. Well, you can say an apple's a fruit, but then a fruit, what's a fruit? And you don't get anywhere, right? Like, a point is that which has no parts. I don't know how meaningful that is. The same concept is I think better explained here. A point is that which has position. These are S's, by the way. For some reason, I don't know if the typewriter was broken or what, but sometimes the S's look like F's. I think it's supposed to be fancy, I don't know. That which has position but not magnitude. To me, that's fair enough, right? You probably have a notion of a point in your mind already, and don't even realize that you do, and that you take it for granted that a point is a real thing, right? Well, bully for you, but I don't know of any evidence to support the idea that such points exist in reality. That is, we human beings have discovered over the years that for anything, anything that we've identified as existing at the smallest level does not have any definite position. So at the lowest level, apparently there are no points. At least, if there are, there's nothing there. There's only a chance that might be something there. But anyway, in the abstract world, it's a pretty simple idea, right? Think of this page, and here's where the finger of this thing is pointing. That's a point on the page. And usually we assign X and Y axes and identify with numbers. That tradition was the introduction of these things came much later, long after Euclid. This was introduced by René Descartes. That's why this says. That's why this says a tribute to Descartes. He invented this system of X's and Y's, and the advantage of doing that meant that you could take problems in geometry and turn them into problems in algebra, and a lot of work had been done in algebra. And if only they could translate geometric problems into algebra, we would have a great tool. And that's exactly what Descartes thought as well. And so he came up with this. It seems like a simple enough idea, but not so simple when you've never seen it before. A graph and points on the graph that have position. That, right? That was a tremendous leap forward. We could now describe certain, categories of shapes and things like a parabola. Instead of having to say, take a focus and draw a straight line, and then imagine a string and so on, or whatever the definition, the geometric definition is. You had an equation. You could write y equals x squared. I can actually draw polynomial functions. Put that to 0. If I wanted to have the x squared function, I just put a 1 here. This here gives me the range that I want to draw the function from. And this is a scaling factor, so the way I've written it here, 75 corresponds to 1. It's probably better to put this at 100 in that case. If I did this, this would go from minus 100 to 100. Let's make that thicker. If you try to delete it, I'm going to change the color. There we go. And in the big view, it looks like this. And then the axes, it looks like this. You see? Now, that doesn't matter to us. We won't be using the axes because we're going to be talking about Euclidean geometry. They didn't have any axes at that time. Now, the way that his geometry works is described as a constructive approach. That is the demonstrations that you see are called constructions. It's like you have a set of tools and then you build something with the tools. You might build a new tool. The tools are given, in fact. There are 2 of them, and it's mentioned explicitly somewhere in here. Where was that? The 2 tools are a straight edge ruler, unmarked straight edge ruler, and a compass. Compasses, that's a thing for drawing circles. Also, without any markings, and that is intentional. Now, where does it say that? Oh, here we go. That's an S again. The straight edge and compass are the only instruments of use, the use of which is permitted in Euclid or plane geometry. To declare this restriction is the object of the postulates. Now, Euclid's geometry is broken down into postulates and then axioms. The postulates are things that are just granted existence, just said to exist, and they correspond to these tools and abilities to do things. Well, the abilities to do things, I guess, define these tools. I've read different breakdowns of Euclid, and as far as the number of postulates and axioms, that seems to vary with what you read, or at least the time frame. This here has this book, okay, which is, I presume, a translation of Euclid, has only 3 postulates, whereas the normal number is 5. I have no connection to the internet, so I can't compare this with something else. I don't have another book that has this in it, but my guess is that in the meantime, after following Euclid's death, and the more people learned about axiomatic systems, this was one of the first. The more they were able to appreciate what was thought to be necessary that was not necessary, and things that were necessary that weren't included. So there are two things apparently that need to be included in this list as well. It's not very obvious, obviously, because I don't remember what they were. And there are 12 axioms listed here in Euclid's version, but by today there are only 5. There are 4 axioms that are clearly things, seem to be clearly things that you couldn't demonstrate by some other means. You just have to state and accept them as true. And there's one that there was lots of debate about over the years, called the parallel postulate. It's an axiom, really, but a lot of people call it the parallel postulate. Not a postulate, it was an axiom, and understood to be an axiom by Euclid when he wrote it down. Otherwise, he would have put it in as a postulate. He understood that it was necessary to state it, and that it could not be proved by any simpler means. And time has proven him to be correct, because systems since have been developed where the parallel postulate or axiom is not true. It's not true in those systems, and those systems are perfectly fine, self-consistent mathematical constructs. Alright, so first it's better to look best one look at the definitions before reading the postulates and axioms. Point, as I said, something that has no parts, or if you like, that picture of the pie with the colored bits, the center point having no color, because it has no extent. It can't be either one of those colors. A line is without breadth. Okay, so something that doesn't have any thickness. It only has extent. A line doesn't have to be straight. It could be a curvy thing. And a curved line is also something without this quality of having breadth. There's width and breadth, if you like, width and height, x and y. In a world where there are 2 dimensions, if another idealized concept, a construct that almost everyone can grasp, can be thought of as the intersection, the division, like this dividing line between these 2 pages. Right? If I brought these 2 pages close enough together, this would shrink and get smaller and smaller and smaller. And if I got them close enough, you would have a line. The definition of a line being the the set of places where it's not this page and not this page. It's in between. Okay. The extremities of a line are points. So here's another look at how you can define a point. If you can imagine a line, then you can imagine what a point is. That's just the end. So there's a point here and there's a point here. Now this is different. This is talking about a straight line. Now it's not the same thing as a line. Sometimes called a right line, not anymore. But one should know that, because if you read old text in maths or physics or whatever, the word right is used in place of straight all over the place. Is that which lies evenly between its extremities. Now here, again, this is just assuming you are a human being and that you have a feel for what evenly means. A human being just knows what that is, and there's no way to really define it. Even mathematically, very difficult to define what evenly means, right? And it would depend on context. I won't get into that. That's a long story. A surface is that which has length and breadth. Okay, so like a coordinate plane, or the surface of the earth, or something like that, piece of paper, those things are surfaces. And the extremities of a surface are lines. That makes sense, right? Here's the page. Here's an extremity of the page. It's a line. Now I got confused over the next two until I realized I thought it was saying the same thing twice, and it is saying the same thing twice, but for two different things. A plane angle is the inclination of two lines to one another in a plane, okay, which meet together but are not in the same direction, like this. A plane rectilinear angle is the inclination of two straight lines, so that's the difference. This one doesn't say straight. Straight lines to one another which meet together but are not in the same straight line. Well, okay, not in the same straight line, not in the same... I'm not really sure why it says not in the same straight line. If there are two of them, right, and they meet, and there's an inclination, I can't see how you could have other than two straight lines, but okay, fair enough. I guess you could have two straight lines that lie on top of each other, but they would have no inclination, and they wouldn't have a place where they meet. They would be meeting at every single point on them. Okay, this is getting long, so I guess I'll split this up into two, and the next one I'll pick it up here on the next definition. Okay, till then.